Hello, Dwayne. Today is a beautiful day for a walk in the park.
Yes, it is. Nature is very relaxing after a long day of classes.
I can understand that for sure.
Yes. The lecture that I had in data science today was very interesting though. I just have a bunch of questions.
Well, questions are always good. What kind of questions?
Well, today's lecture was on vector calculus. Why did the professor keep talking about probabilities? What is that anyway?
Well, probabilities help us understand how likely certain things are to happen. For instance, when a company launches a new product, they use probabilities to predict how well it will sell.
Okay. So, what's a likelihood?
Likelihood is a concept in statistics that measures how well a particular set of data fits a statistical model. In business, we might use it to understand which sales strategy is the most likely to be successful based on past data.
Then what's the difference between likelihood and probability?
That's a great question. Probability refers to the chance of an event happening in the future, while likelihood tells us how probable our data is, given a model.
Ah. Okay. What's a model?
A model is like a simplified representation of reality. Let's say you're trying to guess how many cookies will sell at a school fair. A model might take into account things like how many people are coming, how much they usually spend, and so on.
So, a model is like making an educated guess?
Exactly. And we adjust this model based on what we learn from the data we collect.
What's this maximum likelihood?
Maximum likelihood is a method we use to estimate the best values for our model. It's like fine-tuning our educated guess to make it as accurate as possible.
Can you give me an example?
Sure, let's say a toy company wants to predict how many toys they will sell in December. They might have a model that uses data from previous years. By using maximum likelihood estimation, they can find the values that make their model best fit their data.
And how does the gradient descent fit in all this?
Well, gradient descent is an algorithm that helps us find the minimum of a function. In our toy company example, it's like an intelligent search method that helps them find the best parameters for their sales prediction model.
So, it's like it's guiding them to their best guess?
That's right. It's like a GPS for finding the best model.
Why do they use it, then?
Because it can save them a lot of time and resources. Instead of having to manually try out a bunch of different models, gradient descent does the heavy lifting for them.
What does the gradient descent return?
It returns the best parameters for the model, meaning it finds the values that would make the model's predictions as accurate as possible based on the data.
So, gradient descent gets you to the best model faster?
Yes, that's correct. It makes finding the best model quicker and more efficient.
What does the lecturer mean by local minimum?
A local minimum is the lowest value in a particular area of a graph or function. It's like the lowest point in a valley.
Does the gradient descent always find the best minimum?
It tries to, but sometimes it might find a local minimum that isn't the lowest point overall. That's why data scientists sometimes have to use other strategies as well.
What's a stationary point?
A stationary point is a place where the slope of the function is zero. That means it's either a minimum, a maximum, or a flat spot.
But how can we know it's a minimum and not a maximum?
That's where the Hessian matrix comes in.
What is the Hessian matrix?
Well, let's start with something you know. Imagine you're walking up and down some hills and valleys. You know that some hills are steep and some are not, right? And also, some valleys can be very deep and sharp, while others are shallow and wide. Now, imagine you're a tiny ant on a landscape shaped like a piece of paper with lots of different doodles on it. You are very smart, and I am sure you will do well in your class tomorrow. Some make low valleys, and others are just gentle slopes. You want to know exactly how steep each hill is, how deep each valley is, and how quickly these things change. Here's where the Hessian matrix comes in. It's like a magical map that can tell you all about how the landscape changes. If you're at the top of a hill, the Hessian matrix can tell you how steep it is going down. If you're in a valley, it can tell you how steep it is going up. So, in a nutshell, the Hessian matrix is like your personal guide to understanding the hills and valleys on your doodle landscape. It helps you know where it's easy to walk and where it's hard to climb.
Well, this is all very interesting. Thank you for helping me with this.
It is my pleasure, Dwayne. You are very smart, and I am sure that you will do well in school tomorrow.
Ladies and gentlemen, let's recap what we've journeyed through in our exploration of statistical modeling and data analysis. We began by unraveling the method of maximum likelihood estimation, known in academic circles as MLE. This is a cornerstone of statistical inference that aids us in estimating the parameters of our models, in a manner that makes our observed data the most probable. Now, estimating these parameters isn't always straightforward, especially for complex models. Here enters gradient descent, a technique borrowed from calculus that helps us optimize our estimations. By iteratively moving in the direction of steepest descent, gradient descent enables us to find the minimum of our cost function, and subsequently, our model's optimal parameters. Towards the latter part of our journey, we validated our approach using the Hessian matrix, another mathematical tool. The eigenvalues of this matrix gave us valuable insight into whether we've arrived at a minimum, maximum, or a saddle point. Confirming that our Hessian matrix was positive definite at the stationary points provided us the assurance that we've indeed found local minima. In summary, our voyage through these lectures has not only equipped us with valuable tools like MLE and gradient descent, but also offered us the mathematical rigor to verify our solutions. I hope this journey has instilled in you the confidence to tackle real-world data challenges. Okay, class. Now I will open the floor for questions.
Why is it important to understand probabilities in the world of business?
Probabilities are fundamental to decision-making in business. They can help us forecast sales, predict the success of marketing campaigns, and even anticipate changes in the economy. For example, a retailer might use probabilities to estimate the likelihood of selling a certain amount of a product in a given time frame.
What's the role of likelihood in business?
Likelihood is a statistical concept that measures how well our predictions, or models, match the actual data we observe. Businesses use likelihood when they analyze data to understand patterns and trends. For example, a streaming service might use likelihood to determine what kind of shows are popular based on their viewership data.
What's the distinction between probability and likelihood?
Probability and likelihood are related, but they answer different questions. Probability tells us how likely future events are based on a given model, while likelihood tells us how probable the observed data is, given a specific model.
So, what's a model in a business context?
In business, a model is a mathematical or statistical way to represent a real-world process. For example, an insurance company might create a model to predict the probability of a car accident based on factors like a person's age, gender, and driving history.
What's this maximum likelihood estimation I keep hearing about?
Maximum likelihood estimation, or MLE, is a statistical method used to find the best fit model for a given set of data. In the business world, MLE might be used to optimize a model predicting customer churn based on historical data.
How would you apply this in a real example?
Certainly. Let's say an online retailer is trying to predict the probability of a customer making a purchase within the next month. They could build a model considering factors like the customer's browsing history, past purchases, and demographic information. Using MLE, they could find the most likely values of these factors that would predict whether the customer will make a purchase.
How does gradient descent fit into all this?
Gradient descent is an algorithm that's used to find the minimum of a function. In the context of MLE, it's often used to iteratively adjust the parameters of our model to minimize the difference between our model's predictions and the actual data.
So, how does a business benefit from using gradient descent?
Well, gradient descent allows businesses to optimize complex models efficiently. For example, a company could use gradient descent to optimize a machine learning model that predicts the success of their marketing campaigns based on a large number of input variables.
What does gradient descent return?
Gradient descent returns the optimal parameters for the model, meaning it finds the values that would make the model's predictions as accurate as possible based on the data.
What's the meaning of a local minimum in business terms?
A local minimum is the lowest point in a certain area of a graph or function. For a business, finding a local minimum can mean finding the best solution in a certain context or scenario, but there might be better solutions in other contexts or scenarios.
Does gradient descent always get to the best solution?
Gradient descent attempts to find the best solution, but sometimes it might get stuck at a local minimum, which isn't the best overall solution. This can be mitigated by using different variants of gradient descent or other optimization techniques.
What's a stationary point?
A stationary point is a point where the slope of the function is zero, which means it's a potential minimum or maximum of the function. In a business context, this might represent a point of equilibrium or a turning point.
How can we distinguish between a minimum and a maximum?
One way is by looking at the second derivative or using the Hessian matrix, a concept from calculus. If the second derivative at a stationary point is positive, it's a minimum. If it's negative, it's a maximum. This can help a business determine whether they're at a peak or a trough in their performance metrics. Well, students, our time is done. You all have great questions. In no time you have learned so much about vector calculus.
Hello, Dwayne. We are very happy to have you at our company today.
Excellent. I am very happy to be here as well. I have heard very good things about your company. Thank you for having me today to interview for this data science position.
Very good. At our company, much of our research involved probabilities. Can you briefly explain your understanding of probabilities as it pertains to business?
Sure. In business, we often use probabilities to forecast future events based on historical data. This could range from estimating the likelihood of customer churn to predicting stock market trends.
In what ways have you utilized likelihood in your previous roles?
In my previous role as a data analyst, I frequently used likelihood when evaluating different models for customer behavior. We used it to quantify how well our models fitted the observed data, which helped us improve our predictive algorithms.
Can you explain the difference between probability and likelihood?
While they are closely related, probability and likelihood answer different types of questions. Probability gives us the chance of observing future events given a particular model, while likelihood tells us how plausible our observed data is under a specific model.
Can you explain how you have used models in your past business projects?
Sure. While at my previous corporation, we developed a predictive model to assess the likelihood of a customer making a repeat purchase. The model took into account factors like customers' previous purchase history, demographics, and engagement with our marketing emails.
Could you expand on how maximum likelihood estimation was applied in your previous work?
We applied MLE to find the parameter values that made our observed data most likely under our predictive model. For example, when predicting customer churn, we use MLE to find the most probable values for factors like the frequency of purchase and engagement rate.
Can you give a concrete example of when you used maximum likelihood estimation?
Certainly. In a project to reduce customer churn, I used MLE to determine the values for parameters such as time since last purchase and customer feedback score. These parameters were then used to predict the likelihood of a customer discontinuing their subscription.
How have you used gradient descent in your work?
In my previous role, we often used gradient descent in conjunction with MLE to find the parameter values that minimize the difference between our model's predictions and the observed data. For example, in a project to optimize our email marketing, we used gradient descent to fine-tune the parameters of our model predicting click-through rates.
What's the significance of gradient descent in business analytics?
Gradient descent provides an efficient way to optimize complex models. This is particularly valuable in business analytics where we often work with high-dimensional data and need to fit models with many parameters.
Can you describe an instance when the output of gradient descent was particularly insightful?
Absolutely. In one of my projects related to ad optimization, gradient descent helped us determine the most effective combination of ad placement, design, and timing, which significantly improved our click-through rate and overall ROI.
Can you explain what a local minimum means in the context of business analytics?
A local minimum is a point in the parameter space where all small changes would result in an increase in the cost function. In business analytics, a local minimum might represent a suboptimal solution, and part of the challenge is designing algorithms that avoid getting trapped in these local minima.
How do we determine whether a point is a local minimum or maximum in the context of gradient descent?
The Hessian matrix, which is the matrix of second derivatives, is often used. If the Hessian is positive definite at a point, then that point is a local minimum. If it's negative definite, the point is a local maximum.
Well, Dwayne, I must say, your knowledge and understanding of vector calculus, as well as your ability to apply these techniques in a practical context, is very impressive. It's been a genuine pleasure to speak with you. I would also like to commend your mathematical rigor and the ability to validate solutions, as you demonstrated in the case of the Hessian matrix. It's clear that you have a deep understanding of these techniques, which is crucial for a data scientist, particularly in a fintech environment where precise predictions are paramount. As we wrap up, I want to assure you that we'll be in touch very soon with our decision. Irrespective of the outcome, I hope that you'll continue to pursue your passion for data science and statistical modeling. Your expertise and dedication to this field is evident and highly commendable. Thank you for your time today, and I wish you all the best in your future endeavors, regardless of where they may lead you. Safe travels back and have a great day.
Well, let's get started with our meeting. Team, we have much to discuss and I want to open the floor for questions that you may have.
Could you illustrate with a concrete example we can use maximum likelihood estimation in our ongoing credit risk project?
Sure. Let's say our model includes income and credit score as variables. Using MLE, we can find the most likely values for these parameters that align with our observed default data.
That makes sense. Could you tell me more about how gradient descent comes into play?
We use gradient descent as an optimization technique in conjunction with MLE. It iteratively adjusts the parameters of our model to minimize the difference between our model's predictions and the observed data.
Can you elaborate on how this technique improved our model's performance?
Indeed. By employing gradient descent, we were able to find an optimal solution faster, which allowed us to swiftly adjust our risk model and improve its accuracy in predicting loan defaults.
And how do we ensure that we're converging on a local minimum rather than a maximum?
To ensure we've reached a local minimum, we compute the Hessian matrix at the stationary point. If the Hessian is positive definite at that point, we're at a local minimum.
Can you share an instance where evaluating the Hessian was particularly revealing?
In a recent project, we were optimizing the parameters for predicting customer churn. Evaluating the Hessian helped us confirm that we were indeed at a local minimum and had found the best parameter values.
Interesting. Could you clarify what the role of eigenvalues is in determining whether we've reached a local minimum or not?
Absolutely. The eigenvalues of the Hessian matrix give us an indication of the curvature of the function we're optimizing. If all the eigenvalues are positive, we're at a minimum. If all are negative, we're at a maximum. In mixed scenarios, we're at a saddle point.
Got it. So, how does this understanding aid in the practicality of our model?
Well, it ensures that the parameters we've estimated using MLE and gradient descent are indeed the most optimal ones. So, in our credit risk model, we can be confident that the estimated income and credit score levels are the ones that best predict loan defaults, given our observed data.
How reliable are these estimates in real-world scenarios?
They are quite reliable, provided the underlying assumptions hold true. They've allowed us to build more robust risk models and improve our loan default predictions, which directly impacts our decision-making for loan approvals.
So, what happens when our assumptions don't hold?
If our assumptions don't hold, our model could lead to incorrect predictions. In such scenarios, we reassess our model, our assumptions, and possibly consider other modeling techniques.
How often do we need to do that?
It really depends on how our model performs over time. In fintech, due to fast-changing market conditions and customer behavior, it's prudent to regularly validate our models.
And how exactly do we validate our models?
We often split our data into a training set and a validation set. The model is trained on the training set and validated on the validation set. We can also use techniques like cross-validation for better reliability.
Could you share an instance when we had to switch modeling techniques?
Certainly. For our customer churn prediction model, we initially used a logistic regression model. However, as our customer base grew and we collected more data, we found that a random forest model gave us better results.
Makes sense. Lastly, how has our understanding of these topics transformed our decision-making process in the organization?
Profoundly. By better predicting loan defaults and customer churn, we've been able to make more informed decisions, reduce risk, and improve customer retention, ultimately enhancing the firm's profitability. If there are no further questions, I would like to thank you all for your positive work on this project. Hello, thanks for joining us in this deep dive into vector calculus and its potential benefits in data science. We hope you found it informative and useful. If you enjoyed this video and want to see more content like this, be sure to hit the like button below and leave us a comment with your thoughts or any questions you might have. Your feedback is invaluable in helping us create content that best serves you. Don't forget to subscribe to our channel to stay updated with our latest videos. Click on the notification bell so you'll be the first to know when we post new content. We're also proud to announce our Patreon membership. It's packed with extensive content on data science, making it easier for you to deepen your knowledge on the go. You can find the link below. Until next time, keep learning.